Okay, only one student is attending the class. Okay, Nilofer, whoever she is. I hope so. Yesterday, you have seen the class. So in that we have completed the unit 9. Okay, so we have seen in that the characteristic roots, characteristic values, and also the Cayley-Hamilton theorem we have completed. Okay. Okay. So unit 10 we have started already. It is quadratic forms. Okay. So in that yesterday I have told the conversion of the quadratic form into matrix form and also matrix form into the quadratic form. Okay. Yesterday we have completed that one. So before even I have told what is a positive definite and also negative definite and also indefinite it is there. So in that, before going to that concept, you have these 3 points are there. If any matrix A is there, which is n cross n, that is, it is a square matrix. So symmetric matrix, then a quadratic form. We know the quadratic form is in the form of X transpose A into X. So in that case, we call it the eigenvalues, whatever you are getting in the problem. If they are called as positive definite if and only if the eigenvalues of A are all positive. Okay. So the lambda, whatever the polynomial you will get, when we'll do A minus delta I, that is determinant of A minus delta I, when you equate to 0, you will get one polynomial. After getting that polynomial, if you do the factorization of that one, you will get the roots. Okay. So we know that the characteristic roots, we call them as eigenvalues. So that eigenvalues, when you are getting all positive values, you may get 2 or 3. It depends on the order of the matrix. If it is a 3 by 3 matrix, means you will get the 3 roots. If it is a 2 by 2 matrix, means you will get 2 roots. Okay. So if all the whatever the roots you are getting, they are positive, then it is called as positive definite. Okay. So if you are getting all the lambda values as negative. Okay. So this type of you may get if only rare problems you'll get all the negative values. So if you're having higher order, that is 3 and 4th order, you may get one positive and one negative. So if you're getting the lambda values all negative, then it is called as negative definite. Okay. So and the third case is we call it as indefinite. Okay. So indefinite means combination of positive and negative. That means you will get one lambda value positive value and another lambda value you will get negative value. Then it is called as indefinite. Okay. So this whatever the points I have given, they will ask even in the multiple choice questions. Okay. So try to remember this one. So what are the definite, positive definite, what are negative definite and what are indefinite? Even they will give short, a small 2 by 2 matrix and they will ask whether given the symmetric matrix is positive definite or negative definite or indefinite. Okay. So in the multiple choice, you will have these 3 options. So if you solve the problem, you can know the answer. Okay. So for solving the problems, these 3 points you have to remember. Okay. So yesterday we have seen one problem on this. So if you remember that problem, that is we got both positive and negative. That is q of x is given as 2x22 minus 2x1 x2 plus 2x1 x3 minus 2x2 x3. Okay. So the matrix of this one is, so directly I am writing this. So it is x1 square is not there. So it is 0. So x2 means here x3 is not there, so 0. So minus x1, x2. So here I have told that for finding the matrix form, if you have to divide whatever the values given in between of other than the diagonal, whatever the values are there, you have to divide with 2. So here this is minus 1. So here you will get minus 1. Next x1, x3 is here 1. And you will get x3, x1 here. And after that you have minus 2, x2, x3. So it is minus 1 and here minus 1. Okay. So for finding the eigenvalues and to show that it is positive definite or negative definite or indefinite, you have to find the determinant of a minus lambda I. Like this question will be given, okay? Positive definite, okay? So now we will find the a minus delta I. So a minus delta I means determinant of this one. Minus 1, 2, minus 1, 1, minus 1, 0, minus lambda. So this is equals to, we got the polynomial, it is lambda cube 2 lambda square minus 3 lambda equals to 0. Okay. So if you take out their lambda common, lambda square minus 2 lambda minus 3 equals to 0. So you will get the lambda values as 0, minus 1, minus 3. Okay. So up till here we have completed yesterday. So here is asking whether it is a positive definite. Okay. So it is not a positive definite. Why? Because here we are not getting all the positive values. So 2 are positive, 1 is negative. So this is a indefinite. Okay. So here you write it is not a positive definite. Therefore, you can write the given quadratic form is a indefinite. Okay. So like this, we have to do the problem. First, you have to write whatever the quadratic form into the matrix form. Then you have to find the characteristic equation. You have to equate it to 0. And whatever the lambda values you are getting, with the help of that lambda values, you have to find whether it is a positive or negative definite. Okay. So you have many problems in exercise and also examples are there. And even you have in MEQ questions. Okay. So in that also you have the problems. So we'll see one more problem on this one. So it is somewhat lengthy one. Just in the shortcut I will tell. Q of x equals to 9x1 square plus 7x2 square plus 11 x cube square plus 8x1 x2 plus 8x1 x3. Okay. So the question is same one, is Q of x a positive definite? Okay. So you write what is the matrix form. So here 9 x1 square is there, x2 x3. So the diagonal is 9, 7, here 11. Okay. So here 8 x1 we have to divide with 2. So you will get here 4 and even here 4. So next we have x1 x3. So here 4 and here 4, but we are not having x2 x3 value. So both the values are 0 here. Okay. Now find the a minus delta I. So a minus delta I means here 9 minus lambda . 9 minus lambda 4, 4. Here also 4, 7 minus lambda 0, 4, 0, 11 minus lambda. Okay. This you equate it to 0. Now when you will find the determinant of this one, you will get 9 minus lambda, okay, into here 7 minus lambda into that is 0, okay. Next we have minus 4 into, so when you take out this column and this row, you will get 4 into 11 minus lambda, and this 4 into 0 is, this is minus 0, okay. Next plus 4 into, so this column and this row, if you eliminate, this is 0, minus 4 into, so this is, you equate it to 0, okay. So now you see, when you simplify this, this is 9 minus lambda, 7 minus lambda. Don't split this one, keep like this only. So here 4 4s are, it is 16. 11 minus lambda. Here also it is minus 16. 7 minus lambda. So if you split this one, you will get very high values, okay. So by this taking common, we can write the, easily find the roots of this given equation, okay. So here 16 is there, 16 is there. If you take out the common, 9 minus lambda, 7 minus lambda, 11 minus lambda, if you take out minus 16 common, you will get 11 minus lambda. Here minus 11 is there. So you will get here minus 7 plus 7, okay. So again what we have, plus 7 minus lambda, okay. So this is, if you keep like this only, 9 minus lambda, 7 minus lambda, 11 minus lambda, minus 16 into 11 plus 7 is 18, minus 2 lambda, okay. So like this also you can solve the any polynomial, okay. So here if you take out 2 common this side, you will get it as 9 minus lambda, 7 minus lambda, 11 minus lambda. So here it is 16 already is there, and you are taking 2 common. So into 2 if you take common, it will be 9 minus lambda. So it is 9 minus lambda, 7 minus lambda, 11 minus lambda. It is minus 32 into 9 minus lambda. Okay, minus 32 into 9 minus lambda. Here 9 minus lambda is common is there. No, if you take out that 9 minus lambda, you will get 7 minus lambda, 11 minus lambda, minus 32. Okay. Now if you simplify the middle part, 9 minus lambda into, this is 77, minus 18 lambda, plus lambda square, minus 32. So again 9 minus lambda, so it is equals to lambda square minus 18 lambda plus 45 equals to 0. Okay, so in between minus 18 is there, and if you multiply these two, you will get 45. So that means 15 3s are 45, no. So if you add 15 and 3, you will get in between 18, and if you multiply that, you will get 45. So when you simplify that, you will get here the values as 9 minus lambda, lambda minus 3, lambda minus 15 equals to 0. So you are able to see this one, and when you equate it to 0, you will get lambda values as 3, 9, 50. Okay, so we have got all the values, positive values. So the given whatever it is there, it is a positive. Here you can write that eigenvalues are positive definite. Eigenvalues are positive definite. Okay, so like this you have to solve the eigenvalues are all positive. Therefore, quadratic form is a positive definite. So like this, we have to solve the problem. Okay. In some cases, this is a very lengthy one, no? So they may ask for even 10 marks problems, or else almost you will get the 5 marks problems. So even whatever the problems are there on quadratic form, they will ask for multiple choice also. So try to practice the example exercise and MVQ questions. Okay. So by this, we are completing the unit 10. So in unit 10, we have completed the quadratic form, matrix form, and finding the eigenvalues to show whether the quadratic form is positive definite, negative definite, and also indefinite. Okay. So when we'll go to the 11th unit, it is a inner product space we have. So in that, first we have to know what is the definition of the inner product space. So if you know the definition of the inner product space, on that the problems will be asked to solve the any given problem to show that whether it is a inner product space or not. And after that you have the theorems are there. So in unit 11 you have the theorems, parallelogram law is there, and also Squart's inequality is there. It is a very important one. This is the 10 marks question. You will get last question. You will have no 12th A and B. So in that is a block 4th one. So in that block, you will get the Squart's inequality. And from the unit 12, you will get the gram skimmed orthogonal process is there. And also Bessel's inequality is there. Okay, from these three, any one theorem, you will get in the 12th question. 12A and B will be there. No? So from these three, you will get the 2 questions. So one, you may have Bessel's inequality, or gram skimmed is there. No, if gram skimmed is there means you will not get the Bessel's and gram skimmed are from 12th unit, and 11th unit you have Squart's inequality is there, and showing any given whatever the vector space is there, V of F, showing that it is an inner product space you will have, and in this you have the Squart's inequality. So 2 problems are there. Any one you will get that for 10 marks. So first you see what is the definition of the inner product space. Inner product space. So in that, if we have already we have seen in the unit 1, V of F represents a vector space if it is satisfied some axioms. So here let V of F be the vector space where F equals to R or C. Here R represents a set of real numbers and C represents a set of complex numbers. So the problems may be asked for the real numbers or else for the complex numbers. And inner product is a function F cross, that is F is a small f is the function which is mapping from V cross V to capital F. Okay, so V cross V means here the field of vectors and F is the field of scalars. Okay, already we have seen in the first unit in the introduction of the vector space what are vectors and what are scalars. Okay, defined by so F of alpha comma beta equals to alpha into beta, or else we can write it as alpha comma beta. So in some books they will write alpha like this also. So whenever V of F is a vector space where F equals to real numbers or complex numbers, and inner product is a function F mapping from V cross V to F, defined by what the function f is defined as alpha comma beta equals to alpha into beta. So we'll represent this, whatever the bracket is there, that is called as the inner product space of alpha and beta. So in some textbooks, instead of this brackets, you will get this one. Okay, this symbol also, it represents the inner product space. So whatever this function is there, if it satisfies the three properties, then we can tell that the given function is having the inner product space. Okay, so that is the first one we have, it is the symmetry. So one more sentence will be there, that is we call it as inner product space if V of f it is satisfying the three postulates are there, or theorems, whatever the axioms are there, or rules, or properties, anything is the same one. Okay, so that three are the first one is the symmetry. Or we call it in some books it is called as conjugate symmetry. Okay, so in this alpha into beta equals to beta into alpha. If f equals to r and alpha into beta equals to beta into alpha, this is the bar we have if f equals to complex numbers. Okay, so if the whatever the function is there, field of scalars, if it is a real numbers, alpha into beta equals to beta into alpha, then it is called as a symmetry. So when they are the complex numbers, alpha into beta equals to beta into alpha, whole bar we are taking. Okay, conjugate, no, conjugate in the sense it represents the bar over there. So if it is a complex numbers, you will have this condition. Symmetry means just it will be like the commutative property A into B equals to B into A. Similarly, alpha into beta is equals to beta into alpha here. Okay, second one is the linearity we have. Okay, linearity is A alpha plus B beta comma gamma equals to A into alpha into gamma plus B into beta into gamma. Okay, so here where A comma B belongs to F and alpha beta gamma belongs to B, that is they are the vectors and these are the scalars. A and small a and B are field of scalars and this is the set of vectors. So second linearity condition is A alpha plus B beta. So whatever here alpha and beta are there, if they you are multiplying with the scalars A and B and you are taking another scalar, it is a gamma. So then if you do the multiplication of that one, then you will get this one, that is A you are taking outside, so alpha into gamma plus B if you take outside beta into gamma. So if you show the right hand side and left hand side conditions both are same, then the second property is satisfied. It is called as a linearity. Okay. Next, third one is non-negativity. Non-negativity. So this is the third property we have. In the two conditions are there. First condition is alpha into alpha is greater than or equals to 0. And second one is alpha into alpha equals to 0. So if and only if alpha equals to 0 vector. Okay. So if these three conditions are satisfied by any given function, then it is called as a inner product space. So first one is the symmetry, second one is the linearity we have, and third one is non-negativity. In that alpha into alpha, same whatever the alpha given in the question, if you do the multiplication of that, whatever the value you are getting, if it is greater than or equals to 0, and the second condition is alpha into alpha, that value is equals to 0 if alpha is any 0 vector. Okay, so this is the definition. So in your examination, they may ask even the definition of the inner product space. Depending on that, you have the problem will be there, one function will be given. So it has to satisfy these three properties. So how you will do? So we'll see one problem. So after that, we'll go to the important questions of the linear algebra. So if you have book, open the book. So if you are not having the textbook, I am writing the page number and even the whatever the question number it is given in your textbook, that I will write. So try to practice all these questions from all the units to score good marks. Okay. So we'll see one problem on the inner product space. So the question will be like this: let u comma v equals to x1 y1 plus 2 x1 y2 plus 2 x2 y1 plus 5 x2 y2. Okay. Show that v2 of R is an inner product space where u equals to x1 comma y1 and v equals to x2 comma y2. Okay. x1 x2 y1 y2. Okay. So whatever we have seen the definition of the inner product space, there we have taken alpha and beta. No, so instead of alpha and beta you can take even u and v also. That is u into v equals to v into u. That is a symmetry property. And if you go to the linearity, it is au plus bv comma, you can take w, uv, w we can take. So w equals to whatever the condition is there, that one. So alpha into alpha means u into u greater than or equals to 0, non-negativity. And second condition is u into u equals to 0 if and only if u is, it is a 0 vector. Okay. So the problems may be asked on u and v or alpha and beta. The same concept is the same one only. Okay. Don't get confusion here. So for solving this one, this is the function given. So whatever the function is there, that is in the form of x1 y1 plus 2 x1 y2 plus 2 x2 y1 plus 5 x2 y2. Okay. U are given as x1 x2 and v is given as v1 y1 y2. We can take w also, we need know, we can take w as z1 and z2. Okay. So first condition is we have to show that it is a symmetry. So for symmetry, so u into v. So we can take first v into v. So that is v into u equals to. So what is v here? V is so here in the given question, u comma v is there. Here we are taking v comma u. In the sense whatever the v elements are there, that you have to write as u elements. So here you will get y1 x1 minus 2 y2 x1 plus 2 y1 x2 plus 5 y2 x2. Just you are interchanging u as v and v as u. Okay. So this is the multiplication. No? So in multiplication AB you can write as BA. So if you again interchange this, you will get x1 y1 minus 2 x1 y2 plus 2 x2 y1 plus 5 x2 y2. So this is same as the given one in the question. So it is equals to u comma v. So v comma u is equals to u comma v means it is the symmetry property, it is satisfied. Okay. Next, second one, we have linearity. For linearity, first will it is in the form of au plus bv comma w. Okay. au plus bv comma w. First we will find au plus bv. So au plus bv is equals to a into what is u is x1 comma x2 and b into what is v is y1 comma y2. So when you multiply this, what you'll get, a x1 here plus b y1 comma a x2 plus b. So this is our au plus bv value. So we need now, here you take let z is equals to, so w no, uv is there, so w is equals to z1 comma z2. Okay, so we'll get now au plus bv comma w equals to, so what is our au plus bv? This is a x1 plus b y1 a x2 plus b y2 comma, what is w here? W is z1 comma z2. Okay, so if you want, you can write here this whole thing as 1 and here z1 comma z2. So but this is in the form of u comma v. This whole thing you take it as u and this is v. Okay, this whatever au plus bv is there, it is u and w is v. Now you put that in this one, that is u into v. So u value is this one and v value whatever w is there, w is z1 into z2. So here au plus bv value is this one. So this is like x1 x2 and this is y1 y2. Okay, so now x1 into y1, so our x1 is this one, that is a x1 plus b y1 into what is y1? Y1 is z1 plus 2 into x1. X1 is a x1 plus b y1 into y2. Y2 is z2. Next we have 2 into x2. X2 is a x2 plus b y2. And what we have, y1. Y1 means here z1 plus 5 into x2. X2 is a x2 plus b y2 and y2. Here y2 is z2. Okay, so whatever the given relation it is there, you have to convert the given linearity here in that form. Okay, so by taking this as x1 x2 and this as y1 and y2, so when you substitute in that, this you have to get, and we know that, so when you take the linearity au plus bv comma w means we have to get as a into u comma w plus b into v comma w. Okay, so this relation it has to satisfy. Okay, now you split this one, you will get it as a into x1 z1. You are able to see, I think so. So plus b y1 z1 plus 2a x1 z2 plus 2b y1 z2. Next plus 2a x2 z1 plus 2b y2 z1 plus 5a x2. Okay, z2 is there here. Plus 5b y2 z2. Okay, so when you split this one and you take a and b as common, you will get it in the form of a into u comma v plus b into v comma w. So it is equals to a, if you take out common, it is x1 z1 and here plus 2 x1 z2 and where here we have, so 2 x2 z1 Next here plus 5 x2 z2. Okay, this when you take out a common. Similarly, if you take out b common, you will get it as y1 z1 plus 2b. So y1 z2. Next b is here plus 2 y2 z1 plus 5 y2 z2. Okay, so now whatever this relation is there, and this relation when you substitute in the given relation u comma v, we can tell that it is the relation of u comma w. What is u? U is x1 x2, and what is w? z1 and z2. Here z1 x1, z2 x1 and x2 z1 is there, so it is the relation of u comma w, and this is the relation of v comma w. V is y1 y2 and w is z1 and z2. When you substitute those values in the given function, you will get these two relations. So this is equals to a into u comma w plus b into v comma w. So it is satisfying the linearity. So last third one is the, just we have to show that u into u is equals to, that is greater than or equals to, and also u dot u is equals to 0. So third one is non-negativity. So non-negativity means u comma v. So alpha no. So u comma u means whatever the given relation is there. It is in the form of x1 y1 plus 2 x1 y2 plus 2 x2 y1 plus 5 x2 y2. That means in place of y1 you have to write the x1 only. Okay. So you will get it as x1 plus 2 x1 plus 2 x2 x1 plus 5 x2 x1. So it is equals to x1 square so here y2 means x2. Okay, so x1 into x1 square, that means here u is x1 x2. That means u into u means you will get here same in place of v is there, no, v is y1 y2, so that also you have to write x1 into x2. So that's why y2 is x2 and here also y2 is x2. So if you add both of them, you will get it as 4x1 x2 plus 5. What is the relation here? So the given relation is x1 y1 plus 2 x1 y2 plus 2 x2 y1 plus 5 x2 y2. Okay, so this is x1 next x1 x2, next 2 into x2 x1, here x2 and y2 is what? x2. So here you will get it as x2 square. Okay, so u into u we are getting x1 square plus 4 x1 x2 plus 5 x2 square. Okay, so we can write this as it is equals to x1 square plus 4 x1 x2 plus 4 x2 square plus x2 square we can write, no? Okay, 4 plus here 1 is 5, you will get the same one. So it is equals to x1 plus 2 x2 whole square, a plus b whole square formula we are writing, plus x2 square. Okay, so that is, if you split this one, x1 square plus 2 to the 4 x2 square, so 4 x2 square and 2ab, no, 2 to 4 x1 x2, so 4 x1 and x2. So this is the expansion of a plus b plus x2 square. So whenever u comma u, whatever the value you are getting, that should be greater than or equals to 0, and also u dot, whatever u dot u you are taking, that is equals to 0. Okay, So here you write it as పోయింది కదా వీడియో ఏం రావట్లేదు ఆడియో వస్తుందా
వస్తుంది కదా వీడియో
light here okay yeah you are unable to get the video here okay so just you see the whatever I am telling try to listen that one so u comma u we got the last answer as x1 plus 2x2 whole square plus x2 square okay so this condition is satisfied when u comma u is equals to 0 so here we get it as x1 plus 2x2 whole square plus x2 is equals to 0 here. So from this you will get the value as that is x1 plus 2x2 whole square or x2 square is equals to 0. So when you substitute in this we will get x1 is equals to x2 equals to 0. So this condition is satisfied if u comma u equals to 0 and from that you are getting x1 and x2 values as 0. Okay. So even third condition is satisfied. It is the non-negative we have. So by this, whatever the given function is there, it is the inner product space. So here you write implies u equals to 0 bar. Therefore, the product defined is an inner product on V3 of R. Hence, V3 of R is a inner product space you write, okay? Therefore, so our is V2 of R is a inner product space. Okay.